Okay, good morning. It's Lois Gray at North Highland College. This is Control and Instrumentation, week 2. I don't know, is there anybody trying to VC in? No, would appear not. It's 9 o'clock now, so I'm guessing we'll just leave the recording on anyway, but there's nobody else listening. Right, so firstly, I have to apologise. Dale forgot to bring the rig up, and I wasn't here to tell him yesterday, so we won't get the Bitronic rig till next week. But I was going to do the coursework, introduce the coursework to you this week anyway. And there is a video on the BLE, so you'll just have to watch the video. And then next week you can get to actually play with the equipment. So the remote students don't get the equipment anyway, they just look at the videos, so you're no worse off than them. But the idea is to have some hardware just to give you a wee chance to play around with it. So we'll go through that today, probably at the end of the lecture. Secondly, just wanted to check if there was any questions from last week. So last week we looked at the sort of steps of designing a control system in not very much detail, just very briefly. So it was like block diagram, model, put in your controller, test various input responses, check what your output is, and tweak your controller using various tuning methods. So that's essentially the steps. So we covered that. We covered open loop and closed loop systems, and we looked at some matrix maths, just to kind of get you up to speed with matrices again, especially for people who hadn't done them before. And that was really all we did last week. So is there any questions about any of that stuff from last week? Good. Okay, that's fine. Of course, if you've got questions during the class, just ask me while I'm doing it. Right, today is going to be quite a tough day. I would say today is probably the most maths class orientated lesson you're going to get, because when you look at actually modelling the systems, that's really a starting point. You cannot start adding controllers or tweaking things until you have a mathematical model ready to be simulated. So today we're going to look at building the mathematical models. It's going to involve algebra, differential equations, Laplace transforms, which include integration. So it's going to be quite a lot of math today, but once you get past today's class, it does get a wee bit easier in future weeks. Okay, so hopefully we'll get that okay. We're going to cover electrical and mechanical systems. I'm also going to show you a wee bit about rotational mechanical systems and some slightly more complex systems like, I think there's a motor, which is obviously electromechanical, and mechanical systems with 2 moving parts. Okay, and the mechanical ones get really complicated as soon as you have 2 moving parts. Well, maybe that's just me, because I'm not really a mechanical person, but I think they're really complicated. Okay, and then I'll also go over a wee bit about integration as well before we do the Laplace part. So I think we'll start just with the systems. So if I switch over to the PC view, I'll just show you what we're doing. I'll turn the lights down so you can see that better. Is that okay? I don't want you to go asleep. I used to take my mother-in-law to the cinema, and as soon as the lights went off, she would go to sleep. So that was a complete waste of time. So your notes are in this control folder still, so we're still looking at control for a few more weeks yet. And we did week 1, so this is the week 2 stuff in here. So I do have a PowerPoint which covers some of the more complex aspects, but I'm going to just do the easier models with you on the board first, I think. Okay, so as usual, there's PowerPoint, notes, lecture video. This is last year's one, but I'll put up this year's one as soon as it's ready. Some additional maths you just have a wee look at. Laplace transforms as well. Yeah, I'm not very sure what that is. I think someone else might have put that up, so same with those. I'm not sure how good those are. That other stuff you don't see. Okay, so we'll just go with the model straight away if everybody's happy with this. So we're modelling mass spring dampers. They are I was going to say we're going to look at second order systems today. The slides go into first order systems as well, so we will cover them as well, but I wanted to concentrate on second order systems because your coursework is going to be a second order system. Right, can you remember what the difference between first order and second order systems was from last week? No. Too much to remember from one week to the next. Okay, first order systems only have one energy storage element, second order systems have 2. That is the difference, okay? So a first order system might be something like an RC circuit, or an RL circuit. Second order system would be a resistor, inductor, capacitor circuit, or a mass spring damper would be the mechanical equivalent. Okay, so we will look at first order systems, and we will look at their response, and that is also relevant to your coursework, but I wanted to do the second order ones first anyway. So. Right. Just leave my notes just. So we'll start with the mass spring damper, because I think mechanical folk find it harder to grasp the electrical stuff than vice versa. So we'll start with one that's easier for them. Now my drawings are rubbish, and I don't apologise for my nose. You just have to bear with them. The mechanical folk prefer B or C for the damper constant coefficient. So I think you're the only mechanical person here. Do you prefer B or C as your damping coefficient?
Sorry,
B or C? But we go for B.
Yeah.
Yeah.
Go on.
And we're going to try and move the mass in this direction by a distance x by pulling it with a force F. Okay, so this is your basic, most simple mass spring damper system, really. There's not really anything more simple. It is a second order system because the mass stores energy and the spring stores energy, the damper dissipates energy. Have you got any ideas what sort of applications that might apply to, like real systems?
I see the wagon in a train. Both of the, I don't know how it's called.
Oh, the
wagons.
bumpers.
Like, not the wagons,
The bumpers when they bump into each other.
Yeah, exactly.
Yeah, exactly, yeah. Spot on, that's true. There's a more common one, I suppose, that most people who have cars. Suspension in your car. Yeah, like your car suspension, your shock absorbers. Or something quite similar. And you can think, we talked last week about the different kind of inputs you could have. And if you think about a car, if it falls into a pothole, like if your wheel falls into a pothole, that's like a step change. It's a very sudden change from one height to another, yeah? Whereas I suppose going around a corner would be more like a ramp change because that's a constant force. Well, pretty constant once you're actually in the corner. And that's applied as you go around. So, you can see why it's important to know how something's going to respond to different types of inputs. Right, the way we work these out, the people who did systems analysis last year will know a wee bit about this, is we obtain the differential equation for the system, generally in the time domain, by thinking about the first principles of each of the individual objects on the diagram. And then later on we will do the Laplace transforms to get it into the Laplace domain. Now we'll start with just the differential equation. So we want to know all the sort of first principles that apply to these different objects. We've got Hooke's law for the spring, which I think is that the force exerted by a spring is equal to the spring constant times the distance the spring moves. Okay, why have I got brackets T?
Time.
Time. So these are functions of time. These vary with time. That's why I've got brackets T there. I think I told you last week, I don't always put the brackets T. Sometimes I miss those off because they start to make the equations very long. But hopefully you will just remember which things are varying with time and which things are constants. So K here is a constant. It's determined by the type of spring, what material it's made of, how strong it is, how many coils it has, things like that. So it's a constant related to that particular spring. X is a variable and F is a variable. Okay, then we've got Newton's two laws. I never remember which one's which, but we've got that the force exerted by the mass. Anyone want to tell me what that is?
Acceleration.
Mass times acceleration? Yeah, good. Somebody's awake. Mass times acceleration, which of course is a function of t. But mass times acceleration we can be written as mass times rate of change of velocity. That's meant to be a v, by the way. I'm not very good at drawing small v's. Which if we... Oh, did that wrong. So that's the slope of the velocity curve, that's the slope of the distance curve. Does that make sense? But anyway, you just have to believe me that that's equivalent to mass times acceleration. Acceleration is the rate of change of velocity, velocity is the rate of change of speed, of distance rather, rate of change of distance. So those are the equations that relate to that. The reason I've done it that way is because when we're modelling this, what we might want to do is we might want to apply a force, either a step change or a ramp or a impulse or something different, and we see how far the mass actually moves and how it moves. Whether it just moves and stops, whether it moves and bounces around a bit, you know, like you might think, yeah, that's quite relevant to a car suspension or a bus suspension. We don't really want it to bounce about. We want it just to move and stay solid. So a sports car, is it going to have less bounce than a bus, for instance? Yeah, so that's what we're trying to do here. And then we've got the final one, which is the damper, which is that the force exerted by a damper is equal to the damping coefficient times the velocity that the damper is moving at. Okay, so those are your fundamental principal equations, yeah, which you should really have come across before at some point. You've all done systems, so even if you're electrical, you should have seen these at some point, I think. A few seconds to copy them down. Okay, the next stage is to draw a free-body diagram, and that doesn't apply to electrical circuits, but for mechanical circuits and mechanical systems, you need to draw a free-body diagram and relate all the forces to each other. So which forces are working in which direction? I've kind of run out of space, so I'm not actually going to do that just now. But if we look just at the maths, you can see there's only this one force operating in that direction to move it, and all the other forces are operating in this direction. Okay? So we can get an equation there where this force in that direction is equal to these forces, or essentially all the forces on that mass equate when you add them algebraically add to zero. So, are you following this okay so far? Yeah? Much maths from Tuesday morning, I suspect. But what you end up with is that the force you've applied is equal to the sum of all these forces. And then, of course, you can put in your actual equations for those. So we've got K. So these are things you need to be able to do, quite common questions in the exam, with slightly more complicated systems too. So you have to be able to do it and you have to understand it as well. So force due to the spring, force due to the mass, force due to the damper. If the mass isn't moving, will be equal to the force applied. Okay? Any questions about that? No, you look very bored. We'll try and get past the maths bit. It honestly isn't that bad. Right, now, I want you to rearrange that to give me x. Who wants to give that a go? Do some algebra to get x from that. Does anyone think they can do that? Mm-hmm. So do you think you can do that? I'll be very impressed if you can. I don't want you to go too far. It's really a bit of a trick question. It's actually really, really difficult to do. Because to get this expression, for instance, to x, you have to do a double integral. you'd have to integrate that twice to get x. To get x here, you'd have to integrate that once. So it's not really very easy. It's a really, really difficult equation to rearrange. And that is the reason we use Laplace transforms. So I'm going to show you a bit about them now. Okay, with Laplace transforms, we can make a complicated equation like this, and all systems will have differential equations that define them. But if you lose Laplace transforms, you end up removing the differential equation, and you just have a nice linear algebraic equation with just normal x's, no derivatives in it. Okay. So I'll do a bit on Laplace transforms now, but remember that that's the equation for this mass spring damper. Okay. So a bit of integration next. Anybody still copying this?
Yeah.
Okay. Right, so this guy Laplace, I think he was a French guy, and it was way back, probably the 18th century, 19th century, came up with this mathematical trick that changes differential equations to linear equations. And you do it by doing an integral from 0 to infinity of the function you want to change. Yeah, so that doesn't represent force anymore, that represents function. And it might be a bit confusing, x, still x, but times okay, so in that equation, ft is the function that you're interested in, so your differential equation, yeah? And it's always a function of time. E is your exponential, your standard exponential term, e to the power of something. S is the Laplace variable. And t is time, obviously. And you're obviously integrating over time. The Laplace variable s is actually a complex number. We're not really going to worry about that too much at this stage, but if you were to see it in... I can't remember exactly, I think it's something like that. It's an imaginary number. It's not only just a complex number, but it's a totally imaginary number. It's just a concept, a mathematical concept made up to enable us to do this. Right, so get you two guys to do something first then. Let's see if you can remember anything about integration at all. You can do that. Yeah. So folk who were here last year, this might not be too bad for who did H&D last year. Folk who did the degree last year might struggle with it a bit. So first of all, is that a definite or an indefinite integration? It's indefinite because it doesn't have any limits, okay? So that means it's going to have an additional term. It's not just going to have a final answer. I'll give you a few minutes and see if you can do that. It's just a number. 5, 4, I just wanted the general. So you either can do it or you can't do it. Are the people that can do it done it? Don't worry if you can't. Just I'm trying to keep you awake. Yeah? Anybody still working on it? No. So the answer to that is x to the n plus 1 over n plus 1 plus a constant that you don't know. Okay, so you can't actually solve that until you have some numbers, but that's the answer to that, yeah? So just believe me if you haven't seen that before. I've not seen it for a long time. Okay. So I'll just show you an example. Supposing at x to the 5 dx, the answer to that would be x to the 6 over 6, plus a constant. Yeah? Okay, that gives you the general idea. There's always some division involved. The one you really need to be able to do, though, is this one. Okay, anyone want to have a go at that? Integrating that. Don't worry about the limits just now. Have some memories now. It's actually quite easy, but it's a method of either knowing it or not knowing it. It's not something you can work out if you don't know it. Robert, you've done it? Yeah? Oh, just make sure people are quite good at maths. Okay, will I give you the answer? Yeah? I'm guessing quite a lot of you've probably forgotten this.
Must be A's. Oh, I can't work. That's not
And the negative there. That's the answer to that. Okay. So knowing that, we can then do our Laplace transforms for any function. Yeah. So we're going to start with something quite easy, just a simple step type input, not the differential equation I showed you earlier. We're not going to have to do the Laplace transforms for the differential equation from scratch. Luckily, Laplace has provided a table, so it makes it a wee bit easier. But we're going to start just to get you into the swing so you understand what's going on, just by looking at some simple functions. So, I'll grab my bit of paper. Any questions about that? Okay. If you've forgotten this stuff, you can find these in any maths book. There's usually like a table of common integrations in a maths book. The Stroud one's quite good, the K.A. Stroud book. Right, so going on from that, let's try and do the Laplace transform. Of a step input. So last week we had a quick look at steps, ramps and things. So let's go for a step input of amplitude 1. Okay, so in the real world, if we look at time, look at amplitude, that particular function, ut, is just going to look like that. Okay, so this is u brackets t function. I'll change to u because that's the standard way that they represent steps. They for some reason always call them a function of u over time. Right, so this one's quite easy, and I think most people would even be able to manage this. So we're going from 0 to infinity, and we're going for f of t times e to the minus st dt. So in this case, it's going to be from 0 to infinity. Ft and ut are interchangeable, so that's a 1 times e to the minus st dt. Okay, so you guys write down the answer to that for me. You don't need to work it out over the limits, just get the basic integration for me to start with. Working hard for a Tuesday morning, it's good. Some people are working hard, Robert's flying through it. You should be able to do that, because I did that just a second ago on the previous screen, yeah? E to the minus st over f. Yeah? We did that a minute ago. You multiply something by 1, you're not changing it. Okay, now we want to put our limits in. And if you remember your integration, you use your top limit first, and then you use your bottom limit. Now, just remembering what exponential functions look like. Multicolored just to keep me details. Right, so t is tending to infinity here, t is 0 here, and that's 1. So that's what your sort of exponential function, or sorry, net inverse exponential function looks like. Yeah? So we can work out without actually having to type stuff into our calculators what that's going to be. If you did want to type it into your calculator, I guess you'd have to put s times infinity with pretty much infinity, so I guess you could type in a really, really big number and take the inverse exponential of that, or e to the minus of that, and see what you got. And you should get 0, or very near to 0. And then you could put in t is 0, 0 times something is always 0, so you could do e to the minus 0 on your calculator, and you should get 1. Okay, but I know just from the curve of this equation that 1 is when t is 0, and 0 is when t is infinity. Okay, so what we're actually doing that's what we'd be putting in the limits, yeah? Following that, okay? If you haven't done integration for a while, you'll have to look it up. And then if we just carry on with that, like I say, something times infinity is just infinity, so that simplifies to that. Because infinity times s is infinity, 0 times s is 0. Yeah, I'm guessing you're going to have to replay these videos, some of you. But... And then if we put our limits in, e to the infinity is 0, so that first term becomes 0. Doesn't matter, it's got a negative sign, doesn't matter, there's an s on the bottom. 0 is 0. Yeah, everything else disappears. And then the minus times the minus becomes a plus. And then e to the 0, what's e to the 0? 1, yeah, so, and after all that long complicated calculation, we find that the Laplace transform of a unit step is simply 1 over s. Okay, and s is a complex imaginary variable that we can't simplify any further from there. Okay, so if you get a table of Laplace transforms, you would actually see that. It would tell you that the transform of a step is 1 over s. And you can do this for any size of step. If you made the step 5, you could do the same idea. And anybody still writing? I'll give you a few seconds to write. Maybe talking a bit too much.
Where does the minus go?
Well, the minus is still there.
On the s. On the s. Divided by.
Oh, I just put it up to there.
Alright.
Okay, so you have a negative on the bottom line. It becomes just a negative for the whole thing, yeah? That's just a kind of maths rule. I mean, guess again, you could try that on your calculator. You could try dividing 1 divided by minus 5 and see what you get. But you'll get a negative number, I'm going to show you. But that was a good question, yeah, because I just kind of moved that without really telling you. It was a bit sneaky. Right, so say that was a step of, let's say it's a step of 5. No, 5 maybe not a number. That was a bit like that. Let's pick a different number. 4. Okay, what would the Laplace transform on the step of 4 be? Gary?
Yeah, that way.
Dunno. Huh? Take a guess?
4 over s.
Yeah. Spot on. Good. Okay.
Go on, Mark.
I think you're going to have that, Gary.
I have no idea what this is.
No idea. Okay, you're going to have to go and study some math.
I'm going to
For
do
this
a lot of
class,
study.
Right. So that's quite an easy Laplace transform. I'm going to show you a slightly more difficult one. I'll show you a ramp transform as well. Of course, you can do the inverse transform by differentiating that, but that's quite difficult, and we don't tend to do that in this class. If you go on to more complex class, you could. Right, any more questions? No? Okay.
I'll be a bird.
So this time, I did say that today is going to be the worst math day. It's not going to get any worse than this. Believe me. Okay, now the function for a ramp is actually t times ut, where ut is your normal step. So this is a ramp. Anyone want to guess what the slope of that ramp would be? If that's the same on normal unity step?
1 or t.
Just one. Yeah, but yeah, good. Okay, ramp with slope 1. Oops. Didn't like that very well, did
I just don't
I? Okay, so basically, if you look at that, time, amplitude. Again, this is an input we're looking at, not really a system, but so a unit time is going to go one step up. That's what I mean by slope of 1. Okay, so in that case, u of t equals 1, and the ramp actually is just represented by t. So we can put that into our equation over here. T e minus s t dt. Now this one's quite difficult, and I wouldn't expect you to have to do this in the exam, but I just wanted to show you how difficult it is and why the tables are quite useful. Okay, so does anybody remember doing, what's it called? Integration by parts? Is that what it's called? I'm not even sure that's what it's called. I think it is that's what it's called. Did any of you do Maths 3 last year?
Yeah.
Yeah, you would have done integration by parts in that, I think.
For sure.
It was quite hard, yeah. The way it works is you can't really integrate that very easily unless you split it up. So you can split it up into 2 bits. Where there's a standard equation for integration by parts, where if you've got 2 functions like that, you can split it up into u, v. It's really well since I've done this. I'm copying off my notes, but v, du. And the trickiest bit, I think, is picking which bit's which. So for this one, I've kind of done it in advance, but what I've done is I've done that. In this case, we're going to say that u is t, so that's that bit. Just do it in different colour. So that's that part, yeah? And the dv bit is e minus st. So I do feel a bit sorry for the people who are taking this as their first unit. At least you guys have done some stuff last year, but
It's really spirit as well for us.
the dv bit e to the minus st. That's why I don't like people doing this first, because it's quite tough. Okay, then we want to just find the du. Obviously, we're going to need du, we're going to need v, and we're going to need u and v separately. So we have u. Yeah, we said u equals t. We have dv. Oh, sorry, no, we don't have dv. We don't have v, we don't have du, and we don't have anything else. So we can get the other bits by just doing our derivatives. So if you do the derivative du, what do you get for that equation there?
T to the square.
Robert?
1.
No. Just dt. Derivative time. Yeah?
You just saw it there.
You do the derivative on one side, you have to do the derivative of the other side. Yeah? Just like any algebra. If you add something to one side, you have to add it to the other side. Integrate one side, integrate the other side. So that's quite easy. And to get this one, to find the v part, what we'll have to do is if we integrate dv, that gives us v, yeah? Integral's the opposite of derivatives. So what we'd have to do is integrate e to the minus st, which you've already done quite a lot. So you should all know that ends up as e to the minus st over s. Okay, so that's what v equals, yeah? V is that. Okay, you can go away and think about that later, I think. But that's basically integrating both sides. Yeah, okay. Right.
That's what I thought.
Okay, so we want to put it all into this form now. So we've got, just carrying on from what we had there.
So minus S for...
Oh, sorry, there should be a minus S. Good. Yeah, that's exactly right. I did that wrong. Good. Thank you. Good. Somebody's following. Quite impressed. I didn't notice that. Okay, so if we put all the terms into our standard integration by parts equation, what's U? Just shout out for me. T. Okay. What's V?
E minus
Minus S T over S. Yeah.
minus
Over minus S. Yeah. Okay. Then we've got minus the integral. What's V? Well, we just did that, didn't we? V is negative e to the minus st over s. So yeah, just move the negative sign up again. And du is dt. Yeah? So sadly we've got still a wee bit more integration to do, but we're getting there. Okay, this bit's finalised. We don't need to do anything with that bit. There's nothing else to do there, so we can rewrite that bit. You can see where your maths comes in now, right? I think this is the unit that uses the most maths. I don't know if mechanical people would agree with that as well, but in my opinion it probably is. Right, so now if we integrate that, we're going to get the top bit doesn't change, and the bottom bit we've got s, so we get s squared, only there's also a negative sign again. So it's actually negative times negative, or negative divided by negative, which gives you a positive. And sorry, I forgot to put the limits on here. We should have limits. 0 to infinity. Because the whole thing was to do with our original equation up here, where we were integrating 0 to infinity. So we do have limits all the way through. Yeah. So we're almost there now. So if we rewrite that. So you can see actually integrating e to the minus something is actually quite easy. It's just the minus times t part always multiplies on the bottom, it always becomes a denominator. It's actually quite straightforward. Right. T over into this. And then if we put our two limits in here, so the first thing you do is put your top limit in. These have changed because obviously they disappear, so that becomes a plus, yeah? Minus divided by minus gives you plus. So if we put infinity into that top bit, e to the minus infinity gives us... I need to scroll up, and I haven't got it on this page. 0, good, okay. So there'll be minus 0 there, that's fine. This is the bit in the brackets. And then if we put e to the minus s times 0, that gives us... t equals 0. What's e to the minus? 1. Yeah, good. Okay. Actually, the whole thing should have been in limits as well. That's also from 0 to infinity as well, I think. So we've got 0. Here we've got minus 1 over s squared. Yeah, if we put the limits in here, this one actually becomes 0 anyway, because if you put infinity, e to the minus infinity becomes 0. So that's 0. And if you put 0 in, you've got a t term here. So 0 times something also gives you 0. So this term actually turns out to be 0. And then you've just got minus minus s squared, so you get 1 over s squared. And that's the Laplace transform of a ramp. So there's a lot of work to get to that. Which is why Laplace probably produced his tables. It's hard to expect anybody to do this every time. Now, that's really the toughest bit, I think. The next bit's quite easy. Okay, any questions about that? I suspect it's something you'll have to go home and have a look at in your own time. Right, you'll be pleased to hear the differential equations are actually a lot easier, and you don't need to do them from scratch. There's some basic rules. The people who did systems analysis probably have seen these before. Shall I go back? You finished, Lee?
I don't think it makes a difference.
What's that?
Yeah.
It's on the video. Hopefully it'll be on the video. So yeah. I don't want to feel like I'm rushing you. Right. If we go right back to our original equation, if you remember, the whole point of doing these Laplace transforms was to simplify that. Now, there's a very straightforward Laplace table. I haven't got it to hand, but if you've got a function in the time domain and you want to convert that to a function in the S domain, S being the Laplace variable, you can get this table of transforms from most books. I'm pretty sure it's in our book here. So you can have things like the function of time does actually just transform to a function of S. We write the functions in the S domain with capital letters, so we can differentiate them from the functions in the time domain. Okay, so that's the first thing. Derivative, like dxt by dt, so let's call it dft by dt. That transforms to S times f of s. Now, if you want to be really clever, you can go away and try and actually do that with the Laplace equation, but I wouldn't suggest you do unless you really like maths. The second order function transforms to s squared times f of s. So hopefully you can see a pattern there. You know, a third order function would be s cubed times the function in the S domain. Fourth order different. You're never going to do fourth order derivatives or differentials. But. And then the only other one, I suppose, that's of some importance is the integral. Oh, that wasn't transforms to f of s over s. So pretty much that's the only one you're ever going to need for your system equations. Transformation of system equations is this little columns here. Right, so I'm set you a little challenge now. Going by this, okay, so looking at this table, instead of a function of t, you've got f of t, you've got x of t. But other than that, it's the same. Try and transform this for me into the S domain. So this is a constant, it won't change. That's a constant, it doesn't change. That's a constant, it doesn't change. So you just need to concentrate on the x brackets t parts. Okay? I'll see if anybody can do this. It's actually really easy, but depends whether you've understood what I've been telling you or not. I guess. So you're replacing all the terms that look like that with terms that look like this. That's all you're doing. Yeah. It's actually, there's not really any maths involved, it's just straightforward replacements. One thing for another.
Jack Cool. Pals. Didn't go for his day, bro. Back. Juniors, eh? Aye. He had one that turned over and up there. Something with week and stuff like that.
Yeah, technicalities. Really that you do.
Soup.
Okay, Okay, do you need to do any rearranging or anything at this stage? Just a straightforward transform? You two haven't even tried it, have you? Any of you?
I'm not going to lie, I never heard of a question.
No, I'm in, like, I'm actually attempting this, aye.
I was coping, I don't even know what we're doing.
You don't even need to know any maths to do this.
No, I don't know what the question was, I was coping something.
Oh, I was asking you to transform this using this table. Yeah. So every time you see a function of time, replace it with the equivalent function of s.
Alright.
So that's
Yeah.
You just call it the.
Okay, maybe you can do it later. The rest will be finished. Yeah, it's actually pretty easy. Okay, so here we've got, all right, that's a capital F because it stands for force, but ignore the fact it's a capital F. That's a function of time, so what's the transform of this first term? F. It just stays as F, yeah. But it's a function of the Laplace transform. That's fine, that's quite easy.
I didn't copy it.
Okay, does the little k change? No, because it's the spring constant, so it's dependent on the type of spring. What does the x brackets t change to?
Capital X brackets.
Capital X brackets s. Great, good. Okay, yeah?
Constant.
Yeah, someone other than Kirsty who obviously can do this. Anyone else? Right, what does the d2x brackets t over dt squared change to?
S squared. F squared.
S squared times x of s, yeah, good. And then the last little term, I've run out of bit of space, there we go. B, does B change?
No.
B is a constant, it's related to the damper, so you can't change that. And dxt by dt becomes... Anyone at this end?
Yes,
Yeah, excellent. S.
Just show me, where is it there?
I ignored that.
Spot on. Okay, great. Now the whole point of doing this is to be able to get what we call a transfer function, which relates how our output, or unknown, changes with our input. In this particular system, our input is the force we're applying, and what we want to see is the effect that has on the distance the mass moves, which is x. So we're trying to rearrange that whole equation to get a transfer function, which we can then model in Simulink.
You're around water, aren't you?
No, doesn't really help. The transfer function we're trying to get is this. And then that would then allow us to model in Simulink a system which has got some terms s. Yeah, we can put our force in and we can see how our mass moves. Okay, so I'm going to let you have a go at doing this, because this is just simple algebra. Take all the common terms together on the right-hand side. So the one you're interested in is x. Rearrange the equation and then do some cross-multiplication to get your division. Okay, now I know that this may be a bit tricky, but it's just basic algebra. Okay? So the first thing is to get brackets and get the x of s out of the brackets. And then some rearrangement.
Just using that table again.
I'm going to go and get a glass of water, actually. That's all right. I'm in cans of water.
That's what you want.
It's too far away.
So far. As actually just before. Good job.
What was the question? Just paint it as probably. What's not bad, not?
Division number, look, if it's the top, so x is 2,
this here. What do you feel? You don't just one over.
Yeah.
Yeah.
That F is actually all we're doing for us already. As it was just one second. Right, okay. So now,
Okay, most people time?
oh yeah, no,
What, about a few more minutes?
not time to do it.
Okay.
We've got a game plan.
Sorry. I jumped the step. I jumped like 3 steps.
Ah.
That
And you're fairly sad today.
I love algebra, I can do that in one step without even thinking about it. I always could. But you have to really like algebra to be able to do stuff like that.
7 minutes left.
Yeah, that's 7 minutes more than I've been recently.
Okay, are you still trying to do this?
Yeah,
Right.
I'm not going to lie, I'm not. I've had the time.
I'll do it in steps, but like I say, some people might be able to do it without individual steps. I'm just going to rub that out for a moment.
Did I say that you got this formula?
Okay, so first thing, we want to take the common term out of a bracket, so remember the brackets S just determines that x is a function of s. They're not 2 separate terms, it's just one term. And we're left with k plus ms squared plus bs. Yeah? Okay, then we could divide both sides by the k plus ms squared plus bs, I guess. That would give us, let's write this out so we've got more space. There's a few different ways of doing the next step, so it's up to you how you do it. But one way of doing it is to divide both sides by that big term there. And in fact, I guess if you wanted to see, if you knew what your force was, you weren't going to do any modelling, you just wanted to see how x changed with a specific force, you could probably just use that equation as it stands, like that. But we actually want to have x over f. So if we divide both sides by f now, we get f of s divided by f of s gives us 1. Oh, that should be an s. Sorry, that was a mistake. Es equals... And that's the thing you can put into Simulink. Okay. I'll actually just show you that just to give you a wee break from the maths for a few minutes before we go into the electrical system. So this is brilliant. We now have a model of that mass spring damper, and we can apply any sort of force to it and see what happens in the virtual world, simulation world, obviously. We can change our mass spring damping coefficients and see how that affects what happens to the mass, how it moves. Yeah, so it's really good. Okay, any questions about any of that? Okay, you either haven't understood it enough to have questions, or you're fine with it, one or the other. I'm not sure which. Right, so if I go into MATLAB now, can you still copying?
Yeah, 2 seconds.
No, I've got it. I've done it.
You're done, okay. So let's go into MATLAB. I know some of you haven't used MATLAB for a while, so what we want really is Simulink. You can do this in MATLAB as well. If anybody's interested, I can show you how to do it in MATLAB. But Simulink's easier because it's block diagrams, so I've already got a Simulink page open here. Should have a library as well. So that little multicoloured box gives us the library. Eventually it will open. Sorry, I should have opened this before we started the class. Okay, so what we're looking for is a transfer. Oh, that's all gone small again. I changed all that. Hold on a minute, let's see if I can just change that back to the size that you can actually see.
It's just a break the research. Very fast. Then before me, just said they got it wrong. Break the trip. They were wanting to bypass it all again. So
So we're not sure what certain drawing actually looks to mean.
Aye.
There's no way to tell without probably the computer into that.
Both, I think.
But you couldn't get bad open ups off the bypass switches. I don't know how we go.
Didn't get any bigger, did it?
We know what's the next step.
Sorry, right, okay, I don't know why that's so small. But anyway, you can search for them up in the search term here. You can search for transfer function. I know it's in this continuous block here. It's this one here, 1 over s plus 1. I don't know how clear that is, it's probably not very clear to you, but we'll see it when I move it. So you just click and drag it, left click and drag it to take it onto your screen here. I think most people have used multisim recently, so. Then you want to, if you're ever presenting these to me, I need to be able to see the equations inside the boxes. So make sure your boxes are big enough. If they just say k, then that doesn't mean anything to me. I have to actually be able to see the equations. So we want to edit this equation. So we had, on the top line we had 1, so that's fine. On the bottom line, I don't know if anyone can remember what we had. We had, switch back to the notepad, I can't actually remember what it was. K, ms squared, bs. Oh yeah, now, when you're modelling these in MATLAB, you've got to rearrange them so that the s squared term is on the furthest side, or the highest power of s is on the left, yeah? I don't know if you remember that from last year, but... So I would need to rewrite that as ms squared plus bs plus k. Later, probably next week, that's a very bad k, but hopefully you knows what that was. Next week I'm going to show you how to relate that to a standard second order system. So we've got m, b and k to put into our brackets. Yeah. Can make this any bigger, not really. We've got m there, b and k. Sorry it's so small. The way it works is MATLAB will put the s terms in, so it knows it's doing a model in the Laplace domain, and it also put plus signs in as well. So you only type in the multipliers of the s terms, yeah? So the multipliers in this case are m, b, and k, with spaces between them. Yeah? Have you done this before?
No.
No? Okay, so this is new to some people. I think some folk have definitely done it before. But... Okay, then hopefully... I can make that font bigger. I don't know, you can't really see that, can you? There must be a way of making that bigger. Hold on a second, try and first. Let's see this sometimes. Sorry, I'm just trying to get a bigger font for you. No, I can't find that. We set it up last week and it was working, but you just have to live with it being small. You can look at it on a video, but you'll be able to see it then. Anyway, what's happened now is hopefully you can see when you look on the video or do it for yourselves, you'll see that it's put ms squared as the first term here in the bottom, and then bs as the next term, and then k as the last term, and it's added the plus signs automatically. Okay, so now we have a system. We can simulate that system. There's a couple of different ways of simulating it. You can add in, let's get the library. We'll do something really simple because I don't want to spend too much time on this. You can add in a source, so let's say a step here. Just connect it up by left clicking, and then we can have a sink. Where's my library? Just put a scope on. There's better ways of simulating it, but we'll just go with this just now. Okay, and I could just click run. Would that work? Would that simulate?
No.
Why not?
Because you need to go to the analysis website.
No values.
No, it's because there's no values. I haven't put any values in for the mass, or the spring constant, or the damping coefficient. So let's type some values in. Normally you would do that on the command page here. So I think last week I told you should always make scripts, but if you're just putting values in, it's fine to do them just in the command window. Yeah, you don't need a script just to add a value. So I don't know, let's go for 2 kilos. I don't know if these are even realistic numbers, but Was the last one B, wasn't it? Actually, probably not very realistic numbers, but they'll do just now. So now we can simulate that. And you're quite right, somebody said, oh, you need to use the analysis tool. The analysis tool is a better way of simulating it, and I'll show you that probably another day. That uses different input and output, but it'll give you better, especially if you're looking for things like frequency analysis, like bone plots. But for the moment, this will do. We're only looking for, why isn't it? Information up there. Undefined functions or variables. I don't like saying that. It's a new version of MATLAB, so I'm not that used to using it, but let's see if this works. I think it should still work. And then we can have a look on our scope and see what happens. So what we put in here was a step. It had a delay of 1, so there was like a lag time of 1 before the step was applied. It started at 0 and it went up to an amplitude of 1. So it's a unity step. We can check on the scope what's actually happened. Hopefully. Is that happening? Yeah. Okay, and here we have a reasonably typical. Let's change the background. I can't remember how you change the background on these.
You're on the right bit, I think.
It's alright like that, can you see that?
No, I think you're on the right bit.
Yeah, I thought it was, but I couldn't figure out. Style, maybe.
And then
I can change that to a different colour, and then I should be able to change figure colour white. No, that didn't work, did it? Axis colours white. That's better. There you go. You can see that better, I think, yeah? So this is a fairly typical response for a second-order system. Yeah, you can see that it reaches a final value. Remember last week I said you had a transient section of the response and a steady-state section of the response. So this part here is the steady-state section. It's reaching a final value. I can tell you it's only reaching 0.2, and we've got an amplitude of 1 in, so it's got quite a lot of loss. It's got a big steady-state error. We would expect it to reach 1. It's got a bit of overshoot, so the mass actually will move and then settle and then move again. Well, it'll move backwards and forwards before it finally settles. So it'll move in the direction it's being pulled, and then it'll move back, and then it'll settle at the... It'll stop moving, yeah? Remember, we're not applying the force all the time. We're just applying a force and then taking it away. Or a sudden change in force and then keeping it constant, rather. That's what I meant there. Okay, so you know you can measure certain things off this. You can measure your rise time, you could measure your overshoot, you measure settling time, and that would really define how that mass was going to perform in the system. So if it was a shock absorber, I guess that's not a bad curve for a shock absorber. Yeah, that's not going to give you a lot of bounce. I'd say that's more like a sports car than a bus. Yeah, the bus is probably going woo, and then settle down. Yeah, does that make sense? Okay, happy with that? So that's how you model it. Now I wanted to show you the equivalent electrical one. We'll do it a bit quicker and not with quite as much maths. So, if we get a new page. This is the last bit, well it's not really the last bit because I want to go through the slides as well, but this is the last bit of complicated maths, I would say. Okay, so again, we'll do a second-order system. So this time we're going to have an inductor and a capacitor in the system. We'll have a voltage here. Call it the source voltage. We'll have a volts drop across the resistor. Volts drop across the inductor. And a volts drop across the capacitor. Okay, and then from Kirchhoff's laws, we know that the sum of potential differences equals the sum of EMFs, yeah? That's from Kirchhoff's voltage law. And then from our first principles, we can relate the voltages to the current flowing through the circuit, and then we could find what happens with the current if we apply a change in voltage. Okay, so it's a series circuit, so it's the same current that flows right around the whole circuit. Let's call it I. current, because I normally what we use for current. Okay, so this side of the equation doesn't change. We can use Ohm's law for VR. Sorry, for that one. Let's give these some values. So that's R, that's L, and that's C. So they could be numbers, but we want to do a model without numbers so that we can change values. So we're going to use variables or constants as letters instead of numbers. Okay, so with Ohm's law, what's the voltage across the resistor? What's Ohm's law? V equals IR. Yeah, so the voltage across the resistor is going to be IR. I'm going to write it the other way around, just so that we can put the thing that's varying with time as the second part of that. Yeah. Okay, voltage across an inductor. Anybody know how that is related to current flowing through an inductor? Or the equation for that? No? Related to the rate of change of voltage? Yeah, I did this with you last week, I think. You need to have a bit better memory, don't you? Yeah? So we can fill that in. L, D, I, T, by dt. I'm trying to remember how we would do the last bit. The last bit you would have... the last one's the current. So V equals... I think we looked at... I don't know, did we look at a table last week that had that? I think we did. No. Okay. Well, normally I would write that the other way around, that I equals 1 over C times dV by dt. But we really want it in that form. Okay. So that's just relating all the voltages to the using Kirchhoff's voltage law, and then converting voltages to currents, because we want to eventually find out how current varies with voltage. What we're trying to get in the end is a transfer function, current over voltage. Like that. Okay, so the next step is to do our Laplace transforms. Does anybody not follow that? Okay, I'm guessing if you don't follow it, it's probably because you don't understand the first principles bit, but you can get them from the table. Okay? Right, so we want to do our Laplace transforms. I'll rewrite the table here for you. So we had E becomes f of s, df t by dt becomes s times f of s. The only other one you need probably is the integral of f t dt becomes over s. Right, so I want you to do the transform of that equation for me. Okay? Check it.
Talk to me.
the way, the little s under the VS bit it just stands for source. It's nothing to do with Laplace transform. Maybe I should have used it from that. Yeah, that just means that's the source voltage. Okay. Just need you to do the transform. You don't need to do the rearranging yet. Have you finished that bit?
No, I don't.
No? Sorry. I think most folk have finished, so we'll just carry on. You'll have to catch up with the video if you haven't. So I'll do this side, so we get B, S as a function of S. Yeah? And like I say, this little s just means source. It's nothing to do with Laplace transform. Okay. Caitlin, what's the next one transform to?
R, I, bracket S.
Great, good. Okay, Gary, what's the next one transform to?
I've got it first year on, there's no point asking me.
There's no point asking you.
Yeah.
You can try and do it just now?
No.
No?
Obviously.
Okay, Lee.
L.
Mm-hmm.
Good start.
F S. As far as I go. I'm just shouting letters. F S.
Okay, nearly there. It's this one. What's missing?
I have no idea.
So that transforms to S times the function. This transforms to...
I have no idea.
Anyone else want to tell me?
Yes.
S times the...
Capital I.
Yeah. Follow that now?
No.
No, you just follow it looking at it on the table, yeah?
Yeah.
Yeah? So it was a derivative? So you've got this extra S term comes in.
Have a look at it.
Okay.
Yes, in the video as well.
Anyone want to do the last bit? Craig.
1 over C times 1 over S I S.
C times 1 over S times I of S. Yeah, that'll do. We can simplify that a little bit. R, I, S plus L, S, I over S plus 1 over... I'm going to write that as SC. But it's the same thing. 1 over C times 1 over S is the same. That's very simple algebra. Okay, next step, try and rearrange that. I'm trying to get I over B. Trying to get that. Okay? Don't worry if you've got fractions on the bottom line either, on your denominator. You can live with fractions on the denominator. You've done that already, haven't you?
Yeah.
I think quite a lot of people probably done it already. You should see some similarities between this system and the mechanical one. I'll do for time, but I think we're okay. Okay, this is actually quite easy. So I think I'll just do this for you. You can figure it out for yourselves at home if you can't do it. So take the I term out of the brackets. And what we're left with is R plus LS plus 1 over SC. I should have done square brackets on both sides, sorry. Okay, and then it's just a matter of some cross multiplying. You end up with something that was quite similar to what we had before with the mechanical system. Oops. put that the wrong way around, but hopefully you can figure out that that's the same thing. Okay, and then we do one wee trick with transfer functions. Don't usually like to have fractions in denominators because they look really untidy and they make it hard to work out. So we probably want to get rid of this fraction here, just multiply everything by SC to get rid of that. I didn't expect you to have done this, but I'm just going to do it for you. There we go. So if we multiply everything by SC, we end up with SC on the top line, and then SC, you can go a bit further actually, but I won't do that just now. S squared LC plus 1. Yeah, so you can figure that out for yourselves. That's just quite simple. It's a wee trick that's quite a good thing to be able to do. And you can model that in MATLAB, so whatever. Okay, so that's pretty much all the main maths that you're going to have to be able to do. I do want to show you a wee bit more for some more complex systems if anyone's interested. It is possible we might have some harder stuff to do, but not. And then we'll go on to looking at the coursework, and that will be everything we'll do today. Right, this is also a second order system. You can always tell if it's a second order system, it'll tend to have an S squared term in it. Yeah? First order systems tend not to have S squared terms. Okay. I'm going to put the PowerPoint on now, I think. I'll skip through quite a lot of the slides because we've done quite a lot with the board. Any questions about what we've done so far? I think Harry's still writing stuff, so
I'm okay, that's fine now.
you sure?
Yeah, done now.
Okay. So, you're not going to really like the maths in this, but you're not going to have to do anything as complicated as this in the exam, so I won't worry too much about it. But I just want to show you how more difficult it gets quite quickly. You don't need to add a lot of elements for it to get pretty tough. Okay, so we'll just click through this. Done that. That's our table of Laplace transforms. You'll find that in the book. So this is quite easy. This is the time domain. This is the S domain, and you just transfer them. Don't worry about any of these F0 minus things. They're not really relevant for you just now. I'm only really interested in this bit here. There's the transforms of all our common inputs. So that's our delta, which was our impulse, which is our amplitude of 1 that dies away straight away. Then we've got our unit step, which goes up to 1 and stays at 1. Then we've got our ramp, which goes up 1 amplitude by 1 time, and so on. That's our parabola. And I've got some other ones here. We've got sine wave, cosine waves, things like that. Yeah. I'm not going to do that because that's really complicated. Okay, that was the... so it must have been this week we were going to look at these. These are the first order equations for each of your different elements in the electrical world. So capacitors, resistors, inductors. So you can either have an equation with voltage equals current or current equals voltage. And I showed you that one. Yeah, I think I showed you... Well, that's just Ohm's law, that's straightforward. And I showed you this one as well, that one. Anyway, we've done those, so we'll just carry on with them. That's our second Laplace domain. We've done that. Skip through that. You should see this is the same equation that we actually came up with, I think. It's been rearranged a wee bit more, but it's the same idea. Okay, so now this is a more complicated one. This is two closed circuits together. I don't know what that might represent, maybe a couple of lighting circuits or something like that. So we use our mesh analysis to get equations for both the loops. In fact, if I switch. Yeah, so mesh analysis gives us these equations. We did that last week. Remember doing that? Where I showed you how to do Kirchhoff's voltage law for each loop and then relate the equations together. We did do it last week. If you can't remember, have a look at the slides or the video. So that's our... okay, they've done this a slightly different way. I would normally do that in the time domain first and then transform it, but what they've actually done is they've done the transformation of the elements. So instead of getting a time domain expression, they've transformed the elements to their equivalent in the Laplace domain. So you can see here the inductor has become S times L, and the capacitor has become 1 over S times C. So that was what we transformed those to. We did that a minute ago again. It might make it a wee bit easier. So we end up with our two equations in the Laplace domain, and then it's really a matter of rearranging them so we've got the unknowns all on one side and the knowns all on the other side, which is what's happened here. So these look really complicated, but they're actually not that bad. And then we can use our matrix algebra to solve this. So again, I showed you that last week. What we'd probably use here is something like Cramer's law. So you find the determinant of this matrix, and then you would replace, to get I1, you would replace this first column with these two, and find the determinant of that, and then to get I2, replace this column with these two, and find the determinant of that, and eventually get a really complicated equation that, using Cramer's law, the determinant for I1 divided by the determinant of that, and then the determinant for I2 divided by that, and that's your system. So I'll show you that, but it's pretty complicated. You can have a look at this in your own time. Go through this and just see if you can follow it at all. So DET stands for determinant, yeah? And it ends up being pretty complicated, but hopefully you can see what that looks like. And then a wee bit of algebra just to rearrange it to get I2 over V. So I don't want to go through that in too much detail. That's our mass spring damper system, equivalent table to the electrical system. We've kind of covered that already. That's the one we did. So we did that already. That's just showing you the Freebody diagrams. We'll skip through that. That's the equation that we ended up getting. Now, I think this is really difficult. Once you get two masses, each mass can move independently of the other. So to analyse this, you have to hold one mass still and look at how the other mass moves, and then hold that mass still and look at how the other one moves, and you get quite a lot of different equations for that. So we get two free body diagrams. This one's related to mass 1 moving due only to its own motion, and this one's mass 1 due to the motion of mass 2. And then you've got to do the same thing for the mass 2 as well. So it very quickly gets quite complicated. You can have a go looking through this though and see if you can figure it out, yeah? I find drawing these the hardest bit, to be honest. Once I've got them, it's easy. And then you relate all the terms. So for this one, we've got a spring pulling the mass that way. We've got, I think that's the damper also pulling that way. We've got the force pushing the mass. We've got the mass itself resisting the push, so it's going that way. That's your mass times acceleration. And then we've also got these terms which are related to the second mass, or the second spring. You see, there's a damper there, FV3, and there's a second spring here, K2. So that's the ones related to the forces being exerted by those two, and so on. I'm not going to go into too much detail with this because I think it's pretty difficult. But it does make sense. If you go through it slowly, you will figure it out. Okay, then you relate them all together and you get your free body diagram for mass 1, and you do the same for mass 2. And then you have a system of equations in the Laplace domain. Yeah, so again, I think what they've done here is they've converted it straight to the Laplace domain without using the time domain at all. So that's where all these k1 times x, and you see these little s's slipping in here. That's because it's already in the Laplace domain before they started analysing. Okay, then relating your forces, two simultaneous equations, and the same idea, convert to matrix form and use your Cramer's law to solve. Yeah. Now it looks really awful, but I guess if you put numbers in, it wouldn't look so bad. So you get something like that. I think we'll just skip through that. People who are really interested in mechanical systems can have a closer look. I don't want to do too much of that. I just wanted to show you can use this same modelling, mathematical modelling, for other types of systems. So you can also do it for rotational systems. So here you've got your basic equations for rotational systems, and obviously you can analyse a rotational system with that. And you can also do it with electromechanical if you combine mechanical and electrical together. So there's one for a motor later on as well. So again, same sort of idea. Spring's just a constant, spring constant. That's your damping coefficient. And this time, if you're talking about rotation, you're talking about inertia, J. And that's torque and angle. So different variables, but the same idea. Again, this tends to get quite difficult because I see the examples in the book don't just have a simple mass spring rotational element in it. They tend to use gears and other rotational elements. So I think it's pretty difficult in the book, this stuff. But, so that's analysing this system here. And you've got to do it the same sort of way you did with the two masses. You've got to look at all the forces on J1 and then all the forces on J2, combine them, get your simultaneous equations and solve that. Again, I'm just going to skip through that, I think, because it's a bit too difficult for me. You guys probably aren't going to manage it either. People who are really into mechanical stuff might like it though. Okay, and then the same sort of idea for a DC motor. So it's a typical schematic. You'll remember last week I said that you start with a plain block diagram, then you go on to a functional block diagram. So I suppose this might be more like your functional block diagram. It's got all your elements in it. It's got rotational motion here. It's got electrical motion here. Field doesn't matter too much. Usually that's fixed, so you can ignore that. Depends on the type of motor. And then looking at the mechanical side of it, we're going to have a force exerted on the thing we're trying to drive. And then, yeah. So that's combining the whole lot. That's kind of the electrical part. That's some sort of interface. I can't remember exactly why that's there. I would have thought those two would have been the same. That's the element that's rotating, and this is the thing that it's trying to rotate. It's damper here. And we didn't really do much more than that. That was all I did there, just to show you. Yeah, so you don't need to worry too much about this unless you're really interested in it, but we're not really going to do that in any detail today. Right. The other thing I wanted to say, sometimes you have nonlinear systems. So what sort of things could cause a nonlinear system?
Disturbances.
Sorry?
Disturbances.
Disturbances, possibly, yeah. Yeah, because they're out with your controls, so we don't really know what effect they're going to have. It could be a linear effect, might be a nonlinear effect. In the mechanical world, what would cause a nonlinearity in the mechanical world? No? Okay, so in kind of systems world, I suppose you might get a lag time. For instance, in a flow system where there's a little bit of lag before the flow builds up to what it's meant to be, or a short amount of time where nothing happens. You could get saturation in the electrical world. I don't know if anybody's ever done anything with amplifiers, but you reach a point where the amplifier can amplify no more, so it doesn't follow a linear function anymore, it just stops. So that's a nonlinearity. I think with the mechanical world, they normally talk about backlash in gears, so that's where the gears don't mesh straight away, I think, isn't it? There's a little bit of a delay before one gear will turn and the other one won't. So there's a bit of a delay before they mesh and start to rotate together. So again, that's a nonlinearity. It's quite a lot of things. All the systems we're looking at, we're assuming are linear, but it's not always true. And what you have to do, if you do get a nonlinearity, what you have to do is restrict the time period that you're looking at, or the input that you're looking at, to a very small fraction of the total input, and just analyse for that little bit. So, for instance, with this one, there's a very nonlinear curve there. So you maybe would just analyse between that point and that point, and in that tiny amount, you can assume it's linear. The way Simulink does it does everything with linear equations. It does it point by point. So it would look at it, if it had a nonlinear system, it would look at each point on that, which is obviously not possible for us to do, but possible for a computer to work out. There's some ideas of nonlinearities there. Okay, and that's what Simulink does. Right, that's the end of the slides. I'm not going to go into any more detail with them because I want to show you the coursework. So, has anybody any questions? It's been quite a long lecture, so I'm probably falling asleep. Let's have a look at coursework, and you can maybe have a look at getting started on this today. So, it's under assignments.
Should be a good football game.
I think I'd already opened it actually down here. So it's just Okay, so the idea is we're going to be looking at a real system. All right, it's not really a real system, it's the Bitronic rig, but it's near enough a real system. We're going to be measuring some data from it. So I've already done this. You can have a look at the video and you'll get the data. If the data's on Blackboard, I'll show you where that is. And then using that data, or using the system, it's up to you. You're going to draw a block diagram and then model each element, or model it as an entire system. You've got a choice. So, if we look at the data, I've got the data open here. The first problem with the data is what we did was we applied a step change to the level control. Okay, so what it is, when you look at the video, you'll see some of you used the rig before as well. There's a bottom tank, there's a pump, there's a couple of valves and flow measurement sensors and things, and then there's a top tank. And with the rig, you can control the flow, you can control the level in the tank. I think you can control the temperature, but we're not doing anything with temperature. And there's various different methods of controlling them. You can control it by varying the voltage to the pump, so the pump pumps faster or slower, or you can control it by varying the valve opening, so that restricts the flow rate or increases the flow rate. And with the level, you can either have a closed loop control, whereby there's a sensor monitoring what the level reaches and telling the pump to stop, or it can just be done as an open loop system, done purely on time, where the pump will pump at a very fast rate, and after a certain amount of time it will start to slow down and reduce the level. So it's up to you to decide what system you think we are demonstrating. There's a few different ways of modelling it. They all work. You can assume it's an open loop system. You can assume it's a closed loop system. You can use the data. You can model it from first principles, looking at the equations for the pump, the pipe work, the tanks. You can ignore the valve, assume that we're not using the valve. Yeah? So that's one way. Or you can use the data, which I think is probably the easier way. So what we've got here is data that we measured with LabVIEW, actually, not with the Bitronic rig, where we did a step change from a level from 0 to 80%. So it wasn't 100%. We asked for a change from 0, tank empty, to 80% full as a step, so a sudden change. And then we monitored how the level actually changed over that time, because there's a level sensor as well. So this column here is the time steps. They're very small, so there's an awful lot of data. And this column here is what the level sensor was reporting. And in fact, when we first started filling the tank, the level sensor was below the 0 mark. So we get a negative voltage here. You can think of that as a percentage, but if you multiply it by 10, so that would be minus 4%, yeah? And then, I think that's it might be minus 0.4, I'll check in a minute. So it stayed pretty much at a negative level for a while, which suggests there was a bit of a lag before it started to fill, yeah? And then, if we scroll down, somewhere down here, it starts to fill around about this point here, yeah? So now it's at 0. So that means the water levels come up to the 0 point, and the sensor's reporting that it's at 0, and then it just carries on filling over a period of time until it reaches 80% or nearly 80%. Okay, so it's 76%. So first of all, looking at that, would there be a steady state error in this system? Yeah, of about 4%. Yeah, we're expecting 80% and it only went to 76. So there's a steady state error. It never goes above 76, right up to the end here. Okay, so if I just swap over to... Right, so a few different ways of... the first thing to do is get a block diagram. So you'll need to watch the video. You'll need to understand what's happening, how the bottom tank, pump, top tank, level sensor, how these all relate to each other, what's giving you the feedback, what's recording the data, yeah? But I think you'll get all that from the video, and we'll have the rig here next week anyway. So the first thing is a block diagram, and then the next thing is to try and get a mathematical representation of the system. So a few different ways of doing that. First one is to use the data. There's too many data measurements, so you'll have to try and find a way of reducing the number of data measurements. Maybe take a measurement every second. So from the data that's there, reduce it down by filtering or... I didn't actually do this last year. It was the students found their own way of doing this. So, using macros or offset functions in Excel. So you'll need to do a wee bit of research into how to use Excel to reduce the amount of the data set. Yeah, I think one measurement per second is enough. So you can do it manually, but it'll take you a long time to scroll through all that data and pick out every 1 second. Easy if you can try and find an automatic way of doing that. Then you could plot that data, again using Excel, so you'll get a nice little graph. If I scroll back to here, the sort of graph you might get will be either something. Now we've not really covered first and second order functions, but I have touched on them. So the sort of graph you might get a graph that does that, or you might get a graph that does that. Okay, so from your graph you might be able to work out whether it's a first order system or a second order system. So which of those do you think is first order and which is second?
First one's first order.
Yeah, good. So you do remember this stuff. I didn't know if I covered that in enough detail, but that would be like a first order system and this would be like a second order system. Now of course it might be neither. If it's neither, you've got a bit of a problem if you're using the data, but to have errors is fine, so long as you justify why you've got the errors and explain that in your coursework. In fact, having errors is quite good because it means you've got to think about why have I got these errors and what can I do to change to make it better. But say you assume it's a first order system, then you can then measure some stuff off the graph. Now I haven't really showed you all this, but you've got things like time constants, which is when it gets to 63.3% of final value. Have I showed you this?
No.
Yeah, I think this was for next week. But we'll get there then. We'll give you a start. Okay. And then going by next week's lecture, which is probably the point we'll be at by then anyway, you can then use a standard function and put your values in from your measurements, and you can use that to represent your system. It might not be very accurate. That's one way. If it's a second order one, obviously there's stuff you can measure there. You can measure rise time, you can measure peak time, you can measure overshoot, and so on. Yeah, and there's also a standard function for second order as well, based on these values. That's next week's lecture, to be honest. So I'm not going to go too much detail with that just now. One or two people are just copying that down. But anyway, so that's one way. That's using the data. So it's minimize the data so you don't have so many data points. Plot the data, determine what type of function it is, or what type of system it is, and then relate it to a standard system of the same type. And get your values from that. The other way of doing it is, there's your standard values, standard functions here. Next week we'll cover those. So. Another way to do it is to do it from first principles. I wouldn't necessarily recommend you do this. Some students did try this last year. The problem with this is you need to have a really good understanding of how each element works. So you need to be able to get transfer function for a pump, for instance. Now, I don't know how easy that is. I've never tried to do that myself. But that is another option. And to be honest, if you did this correctly, you'd get a far more accurate model. But it's going to be quite difficult mathematically because you've got each element modeled separately. So that's another option. And then the third option is there is actually the version of MATLAB we have, which is pretty powerful, has got a thing called the Systems Identification Toolbox, whereby you can enter Excel data. You will need to add another column to show your step function, but you can enter input data and output data, and MATLAB will work out a transfer function relating the two elements of data together. For that. Now I can't deal with the non-linearities, so I'm not sure how accurate that will be. There might be some errors in that as well. But I've got the commands, some of the commands here if you want to have a go at doing that. You might end up with a more accurate model. So what you do is you follow this through, and when you do this part, you'll end up with a transfer function in the S domain with S domain parameters, and of course you can then go on to use that as your mathematical model instead. So it's letting MATLAB do all the work for you, really, which is really clever. But there you go. Okay, so going back to the coursework, I don't think you'll get much further than that in the next couple of weeks. Let's do that. Modelling it, testing it, of course, to check that it does actually do the same thing as the real system does, that you do get the same rise times, the same settling times, the same steady state errors with your model, because there's no point carrying on if you don't. I've got to say, most cases you probably won't. There will be some errors. At that point, you need to explain why you think there's errors and justify how you could possibly correct them. You don't necessarily have to correct them. You won't lose marks for not correcting them so long as you explain that you've noticed that you've seen them and you've got some understanding of why you got them. And then doing some tests with a step input. Yeah. And then this next bit I'll maybe explain later, but the idea is that you're going to incorporate a PID controller to get rid of any, or to improve the system essentially, so that it fills up faster, it doesn't overshoot. Yeah. With it being just a level control, the improvements are quite minimal because it's obviously got the limited speed at which it can fill anyway. But that's the idea. And if we have time at the end, it's not really part of the coursework, we could try putting in your PID parameters. PID stands for proportional integral derivative. I think you've done this before. You can try putting them into the real system and we'll see if it does actually improve the speed. The only thing you can really improve is the speed at which it fills, I think. I'm not sure you can really improve much else. Obviously, if it overshoots, you can get rid of that as well, but I'm not sure if it does overshoot or not. Okay, and then this last two bits are to do with frequency analysis, which I haven't done yet. So the way it will work is you'll be starting the coursework before we've necessarily covered all the theory for it, but I always feel that you're always better to start early with coursework, so it gives you a wee bit more time to get them finished and to get your reports written up and stuff as well. Okay, hunting date's quite late for this. It's the 22nd of October, and that's mainly because I'm going to be in China for the holidays in 1 week, around about that time, so I didn't want you handing courseworks in just before I went off. So you've got a few extra weeks from what you'd normally have here. The second one I'll talk about later. Right, as well as today, so you've got coursework to look at now. You've also still got questions. So you had questions last week from the book. I think this week's ones are also from the book. No, that was nothing. So this week too, self-assessment questions. These are building up your knowledge for the exam and also for the coursework as well, but mostly for the exam. As I said last week, just do the problems I've highlighted here. So there's not a lot of problems. They're actually quite easy if you followed any of the theory I've done today. Looking at this lot, I'm not sure if they have, but you'll figure it out.
Not done this maths in 2 years.
No, I know it's hard.
Got some slack then.
I did tell you the maths is really hard in this class. You won't be running into straight. Yeah, but these questions aren't too bad. They're actually quite easy. If you want to do some of the more difficult ones, that's fine. I wouldn't say you necessarily need to do these MATLAB ones either, unless you want some practice with MATLAB. Okay. So that's pretty much it for today in terms of me talking. It's a matter of you trying to do some work now, yeah? Okay, does everyone feel all right? Yeah, we have a break now anyway. Like. Sure. And I'll try and put the video up tomorrow. So I'll just come out of that. Anyone got any questions? We'll have no doubt when we get started.
This call has been disconnected. Thank you for joining.